Objective 8.2, using exponential growth models. In this objective, we're going to take the exponential growth model that we talked about last objective and use it to set up and solve real-life problems. So let's start with the actual model again. Here's another look at what we talked about in the last objective, the fact that an exponential growth model usually looks like y equals a times b to the x. And we said that our b would have to be greater than 1 in order for it to be growth. Okay? However, there is another form of this model that is actually used more often when we're talking about solving real-life problems. And it looks like this. Now, it may look a bit different, but if you really start to compare the two, you'll notice that it's actually quite similar. First of all, we still have A, and A, we still have the A. The B is now become this 1 plus R, this piece that's inside of the parentheses. The A is still called the initial amount. Okay, so in the problem, this A is going to represent whatever the amount is that we start with before growth starts to take place. What's inside of the parentheses, the 1 plus R, that is still called the growth factor. Just like the B was in our model in the last objective, this 1 plus R is also called the growth factor because that's what's replacing the B in this new model. And to be a growth factor, that is now what has to be greater than 1, that 1 plus R. The R itself is called a growth rate. Okay, and it has to be a number somewhere between 0 and 1. And then the T is being used instead of the X, but it still represents our independent variable. The reason they use T now is because usually when we're talking about exponential growth problems, we're talking about growth that happens over time, and the time is our independent variable. So just to help us to know what goes where, instead of using X for the exponent, we're using T for the exponent to represent time period. Okay, now both of these forms of the model have its place. This form is probably more often used because it is more likely that an exponential growth problem will tell you that the growth is happening by some percentage rate. You have 5% growth or you have 20% growth. Okay, and when that happens, we need to use this form of the exponential model because we're being given a rate. So that percent that we're being given, we have to change that to a decimal so that it will end up being between 0 and 1. And then we put that decimal in place for R to come up with our growth factor. So by adding it to 1, we end up with a number that will be bigger than 1 so that we have a growth factor. So basically, any time that you are told growth as a percentage rate, you're going to want to use this form of the equation. But you can also use this form. And usually that's in cases where instead of a percentage rate of growth, you're told that the growth doubles or that the growth triples. So in other words, you're multiplying by 2 each time, or you're multiplying by 3 each time. And in those cases, you want to use this form of the model, because whatever that growth rate is, the 2 for doubling or the 3 for tripling, that's what your B value will be right here. Okay, so probably about 90% of the time we're going to use this form in our problems, but we do occasionally use this form and we need to look out for those situations. All right, so let's actually look at a problem here. It says that the owner of a 1953 Hudson Hornet convertible car sold the car at an auction. So this is an old classic car being sold at an auction. The owner bought the car in 1984 when its value was, sorry about that, $11,000. So that's basically what he bought it for. The value of the car increased at a rate of 6.9% per year. That should be perking up some ideas right about now. We'll come back to that in a second. So, the first thing we're asked to do is to write a function that models the value of the car over time. So, the first thing you should do is ask yourself which of those two models we should use. That's where this comes in. Because we're being told that our percentage rate is 6.9% per year, that tells us that we want to use the y equals a times 1 plus r to the t form. That percentage rate tells us this form. Okay, so in this form we need a and we need r. So a is the initial amount. What is the initial amount in this problem? Well, the initial amount is going to be what was the value of the car at the beginning of this time period. And that is the $11,000 right there. So 11,000 is going to be our initial amount, and that will go in for A. And then what is the growth rate? Well, that's going to be our percent, but changed into a decimal. So our growth rate is actually going to be 0.069. Okay, so once you've identified those three pieces, which model to use, what's the initial amount, what's the growth rate, then we're ready to substitute it into the equation, into the form of the model, in order to get the specific equation for this problem. Now, keep in mind, this is still a problem that represents over time, because we don't have a time value yet. So this is the model that represents the value of the car over time. Okay, now I can use this to answer the next question. If the auction took place in 2004, what was the approximate value of the car at the time of the auction? Round your answer to the nearest dollar. Okay, so now what would we put in for the T if the auction is taking place in 2004? Well, since the beginning of this whole scenario started in 1984, 2004 would be 20 years later, and therefore 20 is going to be our time value. So 20 goes in for T. Everything else is still the same. And now we're going to use our calculator to come up with an answer of about $41,778. So over 20 years, the value of the car went from the $11,000 to $41,778. Okay, so now try one on your own. You have 12 bacteria in a petri dish. After observing for a while, you realize that the bacteria double in number every hour. Write a function that models the number of bacteria over time. How many bacteria would be in the petri dish after 8 hours? Please realize this is a two-part problem. You are first asked to write the function that models the number of bacteria over time. So do that part first, then use that, use that to answer the question, how many bacteria would there be after 8 hours? Pause the video for a moment while you work on this, and then come back and check your answer. All right, so here is a case where we would actually use the first form of the exponential growth model because we're told that the number is doubling every hour. So instead of the 1 plus r form, we would just use the b to the x form because we don't have a percentage rate. We're just told that things double. So that means the b, the growth rate is going to be, the growth factor is going to be 2. Our initial amount is that 12, so that goes there. And then the x or the t up here is going to represent the time, which in this case will be hours. So this is the answer to your first part here. This is the function that represents number of bacteria over time. And then when you put 8 in for the x and work it out, you'll have 3,072 bacteria in 82 hours, or in 8 hours. Okay, let's take a look at a couple more here. This is a very common type of problem that we would use exponential functions for, and that has to do with compound interest. Now, just as a quick reminder, compound interest is when you take an amount of money and then after a certain amount of time, let's say every year, you actually calculate the interest after that 1 year, add the interest to the amount that you had, and then start the next year collecting interest. So you're collecting interest on just a little bit more money the second year. And then at the end of the second year, you stop, you figure out the interest, you add it to what's called the principal, which was the amount that you had, and then you keep doing that. Okay? So you're compounding and you keep adding a little bit more to your amount so that the next time you're figuring out interest, you've got a little bit more to work with. Okay? All right, so here's a pretty simple example of that. You put $250 in a savings account that earns 4% annual interest compounded yearly. You do not make any deposits or withdrawals, so you're just letting it sit there and do its thing. Write a function that models the amount in the account over time. Okay, so again, let's go through those 3 questions that we did in example 1. Your first question would be, which model should you use? Well, again, because you're told that you're compounding at 4% annual interest, that's their way of telling you how much your money is going to grow every time they compound it. And so since that's a percent, we're back to using the y equals a times 1 plus r to the t model. So then what's going to be our initial amount? That's going to be the $250 that we're putting into the account. And what's going to be the growth rate? That's going to be the 4%, which we change into the decimal 0.04. So now we put those numbers into our model, and that gives us the function that represents the amount in the account over time. Because again, we don't know a t yet, so this is over time. Now, if I want to answer a specific question like how much money will be in your account in 5 years, then I can substitute 5 in for t, work it out on a calculator, and I should have about $304 in the account after 5 years. Okay, now that's a pretty simple problem because compounding annually at the end of every year is the simplest kind of compound interest you can do. But there is more advanced compound interest, and so let's just take a look at that for a second. This is what we were using when we were compounding annually. Okay, it's just our exponential growth model with A representing our initial amount. R is going to be our annual percentage rate, sometimes called the APR when you're talking about compound interest, and T is going to represent the number of years. Okay? But what if we want to compound on some other timetable? Okay, then things get a little bit more complicated. Basically, the biggest difference happens here and happens here. Okay? Usually, we compound other than annually in an amount that is less than a year. So you can compound quarterly, which means 4 times a year, or you can compound monthly, or you can compound daily. Okay? And so the number of times that you're going to compound in 1 year is now going to be an n value. And so that annual percentage rate that we had up in this version, we now have to divide that in order to make it a rate for each period. So we no longer want the rate for the whole year, we want the rate for the period. And then here, instead of just number of years for t, since we are compounding more than once in a year, we need to multiply the t times n to get the actual total number of periods that we're compounding. So for example, if I wanted to compound quarterly, sorry, this is really kind of messy. Let me try that again. Okay, quarterly means 4 times per year. And so 4 is going to become my n. Now, if I have a particular rate, which is an annual percentage rate, I now need to divide that by 4 to get the rate for each quarter. And then however many years I'm going to let the money sit, I now have to multiply that by 4 in order to tell how many total number of periods my money is going to compound. Okay, so let's take a look at an example of that. It says you deposit $4,000 in an account that pays 2.92% annual interest. Find the balance after 1 year if the interest is compounded with the given frequency. So we want to figure out quarterly, and then we want to figure out daily. So as we were just talking about, if I want to figure out quarterly, that means my n is going to equal 4. For daily, we usually use an n of 365, although sometimes banks and different institutions will use 360. But we're going to use 365 for daily. Okay, so let's work out quarterly first. Based on our problem, our initial amount is the $4,000 that we're putting into the account. Our annual percentage rate is the 2.92%, which will be changed to the decimal 0.0292. The time is the number of years, and we're just interested in 1 year. And the n, as we just said, is going to be 4. So when we substitute all of that into the advanced compound interest formula, we've got our 4,000 here for initial amount. We still have our 1 here, but now we're taking the r divided by 4 so that this represents the rate per quarter. And then since we're compounding quarterly, in 1 year's time, we're actually compounding 4 times. So we need to take the 1 times the 4 up here to get the total number of periods that we're compounding. And so now, when you work that all out, you end up with about $4,118.09 in the account after just 1 year. So you've earned about just less than $120. All right, now let's do the same thing with the daily. The only thing about our information and our formula that's going to change is the N. It's still the same initial amount of 4,000. It's still the same annual interest rate of 0.0292. It's still the same number of years, 1 year. But now we're talking about an N of 365. Excuse me. So when we substitute all of this into our formula and then work it out, we end up with $4,118.52. So as you can see, in just 1 year, oops, sorry guys, I don't know if you noticed this or not, but this right here, that should be a 365. Okay, so let me just recalculate that quick, make sure our answer is right. All right, so we're taking 4,000 times 1.00008 and raising that to the 365 power. Yep, so it's still correct, $4,118.52. So you can see in just 1 year's time, there's not much difference as to how much you can make. It's just a few cents difference. But the longer you leave this money sit, and the more times it has to compound the interest, the more money you're going to be able to save, and the more you're going to be able to compound your interest. Okay, so try another one on your own. I'll let you read the problem this time, so go ahead and pause your video for a moment, read through the problem, set up the equations that you need, and then come back and check your answer when you're ready. Okay, so for 5 years, if you have $500, that's your initial amount. You're paying 3% annual interest, so that's your R. Compounded monthly, so that means your N is going to be 12. And in the first case, they're asking you how much would you have in 5 years, so you would need to take 5 times 12 up here in the exponent. When you work that all out, you end up with about $580.81. Now if we do the same thing for 10 years, notice again the A, the R, and the N in this case are all the same, but we've changed the T here in the exponent. So now we're going 120 compounded times, and when we work that out, we end up with $674.68. So after 5 years, we've gained about $80, but after 10 years, we've gained about $175. So hopefully you're starting to see how, when we're talking about compound interest, time is definitely your best friend. The longer you can keep something going with compound interest, the more and more and more you're going to earn. And that's what makes it an exponential growth function. All right, so hopefully that gives you enough information to be able to use on your practice sheet. So in class, you'll be able to work on the 8.2 practice. Please make sure you ask questions during class if you're unsure about anything from this video. And when you've completed the 8.2 practice, make sure you get it checked off by Mrs. Gordon. We'll see you next class.